So this chapter is basically the chapter on closed systems. Our focus on this chapter would be the energy analysis of closed systems, and what we'll be specifically looking into this chapter. This is the outline of the chapter that we'll be looking into. We'll be looking into the boundary work, which is one form of the work associated with moving boundaries. Boundary work is normally recognized as PDV work, and this work is normally encountered in reciprocating devices, which is automotive engines and compressors. So the first thing that we'll do is we'll assess the boundary work. Then we'll analyze that the first law of thermodynamics is the conservation of energy principles for closed systems. We'll apply this law and develop a balance equations for closed systems. We'll also be looking into the specific heats at constant volume and constant pressure. So we'll be looking into CP and CV. We'll try to understand what is CP and CV, and we'll relate these specific heats to the changes in internal energy and the enthalpy of ideal gases. So we'll be using the CP and CV values for internal energy and enthalpy of ideal gases, and then we'll also understand the changes in internal energy and enthalpy of incompressible substance. How do we determine the internal energy and enthalpy of incompressible substances? Incompressible substances basically means solid and liquids, where there is no change in the density with the pressure. And we'll apply the energy balance equation, and we'll solve some of the examples for closed systems which involve heat and work interactions for three kinds of substances: the pure substances, ideal gases, and the incompressible substances. So this will be covered in this chapter 4. This is the outline of what we'll cover in chapter 4. Beginning with the boundary work or PDB work, which is commonly encountered in automotive engines and compressors, let us first understand what is PDV work. In a closed system, where you have one of the boundary as a movable boundary, as the boundary moves, there is some work associated with the movement of the boundary, and this work is known as boundary work. From the perspective of thermodynamic analysis, the engines which normally encounters boundary work or real engines, they move at very high speeds. And when they move at very high speeds, it is very difficult to attain equilibrium within the system. And therefore, the thermodynamic analysis alone is not sufficient enough to exactly determine the work associated with the movement of the boundary. As the system is moving very fast, as this piston is moving very fast, equilibrium within this system is not established. And since the equilibrium is not established, you cannot determine the boundary work from the thermodynamic analysis. Why? Because when the system is moving very fast, you cannot say whether the system has a uniform pressure or not. Pressure near to the piston would be relatively higher as compared to the pressure at the lower end when the system is moving very fast in case of real engines. So thermodynamic analysis cannot be performed. Why it cannot be performed? Because you cannot represent the pressure. If this is the pressure specific volume plot or pressure volume plot, if I have to specify the state of my system at this point state, I cannot say whether my pressure is this or my pressure is this or this, as I don't have any uniform pressure within the system when the system is moving very fast. So if I cannot specify the pressure of my system, if I cannot specify the pressure of my system and my system moves from, let's say, if my system moves from, let's say, this state, which is state 1, to some other state, state 2, I cannot represent the path through which this system moved from 1 to 2. I cannot say whether my system moved from this path or what path was used to achieve state 2. And as you know that work is a path function, you cannot analytically solve this without the knowledge of the path. Therefore, for real engines, the boundary work is normally determined by direct experimental measurements. You cannot determine the work by thermodynamic relationships. However, in a quasi-equilibrium process, the quasi-equilibrium process is a process in which your system is in equilibrium at all times, or is nearly at equilibrium at all times. That means the pressure within the system is uniform throughout the time, and that there is no pressure gradient within the system. This takes place in a quasi-equilibrium process or quasi-static process, and real engines approach a quasi-equilibrium, quasi-static process at low velocities. So at low velocities, you can use the thermodynamic relationships to assess the work done during the movement of the piston or moving of the boundary. Now, how do you determine uh, the boundary work done associated with quasi-static or quasi-equilibrium process? Let's say your system is at was initially at this position, and due to the application of uniform pressure, which is occurring at low velocities, your system moved from one state to another state. Your system moved a distance of ds under the application of force F acting on this cross-sectional area. Now, if I have to determine the differential amount of work done as a result of this differential displacement, this is basically due to the expansion and compression of the expansion or compression of your piston cylinder assembly. The differential amount of work done by the gas is basically specified by inexact differential. Capital letter W specifying the boundary work, and B is a subscript which again is used for the boundary work. And this is done when the piston moves by a differential amount ds. So the boundary work is essentially equal to this differential amount of boundary work is equal to the force multiplied by the differential distance ds. And force is nothing but it is pressure into area. We can take the pressure P because you assume the system to be in equilibrium, or you assume the process to be quasi-static process. And A into ds is nothing but the change in differential volume. A is constant, ds is the distance moved by the piston. So A into ds is the differential volume in change. Now, this is the differential work done as your piston moved a very small distance of ds. If your system moved from, let's say, 1 to 0.3, what is the total amount of work done? The total amount of work done as your system moves from two states, or the total amount of boundary work, is basically the integral of 1 to 2 for PdV. So you have to integrate PdV from 1 to 2 in order to calculate the total boundary work. How do you do that? In order to in order to assess PdV, the first thing you should know is that if boundary work is positive, that represents expansion. If the boundary work is negative, it represents compression. And in order to evaluate PdV, you need to have a relationship between pressure and volume in order to find out the boundary work. And the relationship between pressure and volume is nothing but the path through which the system is moving. So the knowledge of pressure as a function of volume is essential in order to calculate the boundary work. And the boundary work as a result of relationship between pressure and volume is nothing but the equation of process path. How did you move from state 1 to state 2? So let's say if I have this pressure and this volume curve, and this is my state 1 and this is my state 2. If I moved this way, path A, or if I moved this way, path B, both would have different relationship between pressure and volume. So in order to have the relationship between pressure and volume, in order to calculate the boundary work, you need to have a relationship between pressure and volume, and that relationship is nothing but the equation of the process path. So let's say if I move from 1 to 2, the small amount of work done, the small amount of area, this small area under the process path, which is dA, is nothing but pressure multiplied by the change in volume. As your system moves from this state to this state, this is change in volume, and this change in volume multiplied by the small pressure, which I assume is constant, is basically the area under the curve. So small area, differential area under the curve is basically the differential work, a small amount of work done as the system move from this state to this state. If I have to compute the total area The total area under the curve would essentially represent the total work done as your system move from 1 to 2. So the total area under the curve A, the total area under the curve A is the integral 1 to 2 dA, which is nothing but the integral of P dV from 1 to 2. So in other words, the total area under the PDV curve as the system moved from state 1 to state 2 represents the total work done. As it is written over here that the area under the process curve on a PV diagram is equal in magnitude to the work done during a quasi-equilibrium expansion or compression process, again for a closed system. So if I have these three curves, these three process paths, let's say the process path A, B, and C, just by looking at it, I can say that the work done for A is the highest as compared to C. Why can I say that? Can anybody specify?
सर डी ए उसका ज़्यादा होगा.
Very good.
area under
Since
the curve.
very good. So it means that the area under the curve for A is the highest. Therefore, the work done for A would be the highest on a pressure volume plot for a closed system. And one thing more from this curve, that if I undergo a cyclic process, that if I go from state 1 to 2 and come back from 2 to 1, or if I go from if I go from state 1 to 2 in this way, following the path B, this is while I am compressing it, I am reducing the volume. And then I come back from again 2 to 1 by path A, and this is essentially expansion. So there would be if A and B are different paths, I would have essentially some network which would be available to me, or some network that would have been done by the system. So this network is what? It is essentially the difference in the area between the two paths that we have done. As I go from 1 to 2 and 2 to 1, I have completed a cycle, and the cyclic process would result in some net amount of work done. Now, depending upon the nature of the cycle, you can say that this network is available to you, or this network has been done by you, depending upon the direction of the cycles. So the network done during a cycle, the network done during a cycle is the difference between the work done by the system and the work done on the system. If I take system from 1 to 2, I am doing work on the system by compressing it. And if the system moves from V2 to V1, that is the system is expanding. So this work is being done by the system. Anyways, in a cyclic process, following two different paths between the same two states, you will have some network available to you. Or work clear enough?
Excuse me, sir.
जी जी.
Though we have some network, but whether you have any change in net energy?
Sorry.
Sir, though we have network, but whether we will have any net energy change?
What is work?
Sir, but we have come to know that the change, the total work done in a closed path is zero.
Sorry, the total work done in a closed system is zero.
Net energy change in a closed path.
Net energy change in a closed path. Net energy change, energy is a state function or a pressure function?
State function.
So if your states are fixed, the net energy change would be what?
Zero.
This means, all right, I'll explain it a little. If you have moved from state 1 to state 2, if you have moved from state 1 to state 2, and then back from state 2 to state 1, the change in energy is what?
Sir, zero.
The change in energy is zero. That means that no new energy can be created. All right. But the heat and work are not zero. All right. The heat and work are not zero. This
यस सर।
would be
सर जो
heat.
नेटवर्क या हीट होती है तो वो कहाँ चली जाती है, जो मतलब वो नेट एनर्जी में तो कंट्रीब्यूशन वो कर नहीं रही।
So उसमें ये हो सकता है ना, Q net equals to work net, जो आपने हीट दी है उसकी वजह से नेटवर्क प्रोड्यूस हुआ है। क्लियर? आपने सिस्टम को हीट दी है, कोई नेट हीट दी है जिसकी वजह से कोई नेटवर्क प्रोड्यूस हुआ
ओके।
है, लेकिन इट इज बेसिकली जस्ट द फॉर्म चेंज इन द फॉर्म ऑफ एनर्जी। कोई नई एनर्जी नहीं हुई है, चेंज इन एनर्जी वुड बी, बट हुआ क्या है, हुआ ये है कि आपने जो हीट दी है उसने कुछ वर्क प्रोड्यूस किया, नेटवर्क प्रोड्यूस किया। क्लियर इनफ? बिकॉज चेंज इन एनर्जी जो
जी
है
सर,
वो तो
ओके।
कंट्रीब्यूट किससे कर रही है, वो तो हीट से कंट्रीब्यूट कर रही है, वर्क से कंट्रीब्यूट कर रही है इन क्लोज सिस्टम। दो फैक्टर्स हैं जो टोटल चेंज इन एनर्जी को कंट्रीब्यूट करते हैं। इफ आई स्टार्ट फ्रॉम 1 to 2 and come back to 1, the change in energy would be zero, but heat and change in work would not be zero.
ओके सर,
Clear?
गॉट इट।
All right.
यस सर, थैंक यू।
Now moving on, you have three different processes that you have to see: polytropic, isothermal, and isobaric process. Again, all associated with the boundary work. We'll have different conditions for it. So in a process which is a constant pressure process which is a constant pressure process, the boundary work would be what? The boundary work is simply, boundary work is PdV. If pressure is constant, P naught would come out of the integral, and you would have just the change in volume multiplied by the constant volume, constant pressure would give you the boundary work WB for a constant pressure process. Is it clear?
यस सर।
All right. Now for expansion and compression processes of gas, the expansion and compression of gas are normally expressed by a generic equation which is PV to the power n is equals to constant. This is a process, or this is known as a polytropic process. A polytropic process. Generally, the expansion and compression of gases follow this relationship, where N and C would determine the path. These two would determine the path, but generally the shape of the path is governed by this equation for the expansion and compression of gases. And for a polytropic process, if when I say a polytropic process, I mean a process which is following this generic equation, PV to the power n equals to constant. This is the relationship. The n value would determine the shape of the path, but if a substance or a fluid or a gas is following a polytropic process, you will have essentially this relationship. In case you have this relationship, what would be the boundary work? Let's say this is a polytropic process. This is the same thing. P v to the power n equals to constant. It is the same thing. If you take v on the other side, it would be p equals to c v to the power minus n. So in case of a polytropic process for a gas, this is a polytropic process. Now PV to the power n is equal to constant. If you change the value of n, your shape of curve would change. But generally, the expansion follows this relationship. So if you have a polytropic process, what is the boundary work done? For a polytropic process, the boundary work done is calculated using this terminology. How do you get to this terminology? Let's say you have PDV as the work. Integral PDV 1 to 2 is the boundary work. This is the boundary work. Now we say that for a polytropic process, if this is a polytropic process, we say pressure is equal to CV to the power minus n. So we can plug in from 1 to 2, instead of pressure, we can plug in CV to the power minus n. dV is the total work done, boundary work. Now, since C is the constant, I can bring it out of the equation. C is out, and now we have to integrate V to the power minus n dV. 1 to 2 is the boundary work. And this I can further write as constant into V to the power minus n plus 1 over minus n plus 1 once I have taken the integral from 1 to 2. And this could be written as C multiplied by V2 minus n plus 1 minus C v to the power v1 to the power minus n plus 1 over whole over minus n plus 1. Is it clear so far? Up to this point, is it clear?
Yes, sir.
All right. Now I can write this expression. If I want to write this expression, I can write it in this form equals to cv to the power minus n multiplied by v2, then this minus, and I can write this expression also in this form c v to the v1 to the power minus n multiplied by v1 whole over 1 minus n. This is the same thing. Is it clear?
Yes, sir.
Now, for if this is the expression, if this is your generic expression, you can say P2 is equals to CV2 to the power minus n and P1 is equals to CV1 to the power minus n. So you can replace this expression over here with P2 and you can replace this expression over here with P1, and essentially you will have for a polytropic process the boundary work is P2 V2 minus P1 V1 whole over 1 minus n. So this n would determine the amount of boundary work or the shape of the curve. Once n determines the shape of the curve, the boundary work would change. Clear enough?
Yes, sir.
All right. So for you, the boundary work for a polytropic process, the boundary work for a polytropic process is basically this expression, which is dependent upon the value of n. Now I say that the fluid which is going through the boundary, the fluid which is going through the polytropic process is also an ideal gas. This is the further classification that the fluid who is undergoing the expansion or compression under polytropic process is an ideal gas. So for an ideal gas, I know that PV is equal to MRT. If the fluid is ideal gas, I can say that PV equals to MRT, or I can say for state 1, P1 V1 is equals to MRT1, and for state 2, P2 V2 is equals to MRT2. Clear enough? Is this clear?
Yes, sir.
So I can also express the boundary work as, instead of writing P2 V2, I can write MRT2. So I can write MRT2 minus MRT1 over 1 minus n is the boundary work for a polytropic process where the fluid is behaving as an ideal gas. Or I can write it as MRT2 minus T1 over 1 minus n is the boundary work for a fluid which is going through polytropic process and behaving as an ideal gas. Clear enough? Is it clear?
Yes, sir.
All right. So this is the boundary work for a polytropic process undergoing an ideal gas. Now let's say my n value is equal to 1. In case my n value is equal to 1, the expression for polytropic process would be PV is equals to constant. Isn't it so?
Yes, sir.
And if I compare this expression for ideal gas, when would ideal gas PV equals to MRT would be equivalent to this? ऐसा कब होगा जब PV is equals to constant for an ideal gas? For an ideal gas, when can I say that PV is equals to constant?
सर एम भी कांस्टेंट आर भी कांस्टेंट जब टेम्परेचर कांस्टेंट होगा.
Very good. So when the ideal gas is going through the isothermal process, we can say that it is equivalent to PV is equals to constant or polytropic process. So for isothermal process, for isothermal process of an ideal gas, we can say that it is undergoing a PV equals to constant process where N is equal to 1. Clear enough?
Yes, sir.
Yes.
All right. All right. So this means that for an ideal gas, I can say that when N is equals to 1, the polytropic process is an isothermal process. That means PV is equals to MR T naught. T naught is constant temperature, which is equivalent to C, or I can write this whole expression as constant. That means I can express pressure PV equals to constant can be expressed as pressure equals to C over V. Clear? If I have this expression with me and I know that the boundary work is integral 1 to 2 P dV, I can write instead of P, I can write C over V. So I can integrate 1 to 2 C over V dV, which I know C is a constant. I can bring it outside and I can write 1 to 2 dV over V. dV over V, the integral of dV over V is what? C multiplied by ln V2 over V1. Is it clear?
Yes, sir.
And you can express C as PV. C is nothing but PV. So you can write over here that boundary work is equivalent to, if I take this expression over here, PV ln V2 over V1. This is the boundary work for an isothermal process undergone by an ideal gas or for a process where your N is equal to 1, a polytropic process where N equals to 1. So for a polytropic process where N is equal to 1, or for an ideal gas undergoing isothermal process, the boundary work is essentially equal to PV ln V2 over V1. Clear enough? So I'll stop over here